All right, we're back. We're on page 9 of Notes 24. We are solving a lot of differential equations if you've been following along or doing notes on your own or whatever. And this video is going to be no exception. So let's see what we can do. Consider the differential equation dy dx equals 2/3 x plus 2y minus 2. So by hand, you would never want to make this slope field. We looked at a lot of slope fields that kind of looked like this one in Notes 23 when we were talking about slope fields. Your calculator can kind of make them, GeoGebra can kind of make them. And it's really interesting to look at the solutions because there's like 3 types of solution curves. Basically what I'm saying is, because we've done a lot of problems like this, I have a really good sense of how this problem is going to go. And that's where you want to get to when you're like studying this stuff. You want to have looked at things often enough that you see it and you're like, oh, I kind of know what's going on here. Because I think I do kind of know what's going on here. So let's see if we can do it. First, find the second derivative in terms of x and y. Always going to say that. You can't leave dy dx in your second derivatives, is basically the rule, I guess. It's like an arbitrary rule, though. There's no reason you couldn't in like other contexts, but AP calculus, you'll never have dy dx in your second derivative. All right, so we're going to take the derivative of, so we're looking at this, right? So we're taking the derivative with respect to x. So, and that's important. So the second derivative with respect to x is the derivative of 2/3 x is just 2/3 plus 2. The derivative of y with respect to x is dy dx. And the derivative of -2 is 0. So now we're not allowed to have a dy dx in our answer, so we're going to replace dy dx with dy dx, which is 2/3 x plus 2y minus 2. So the second derivative is going to be 2/3 plus 2 times, and now we replace it, 2/3 x plus 2y minus 2. And I think we should clean that up somewhat. Okay, so I guess I'll do it. You know, I just want to like move this up and do it right underneath. So I'm going to do that. Okay, here we go. Clean it up. Also, sometimes I just stall when I don't feel like doing things. And a really good way, it's like when you clean your room to avoid doing something. A good way to stall is to like move things around. All right, so 4/3 x plus 4y. And then minus 4 plus 2/3. So minus 12/3 plus 2/3, say minus 10/3. I believe that is our second derivative. I believe. Maybe I should check that again. 4/3 x, 4y, 100%, minus 4 plus 2/3, minus 12/3 plus 2 minus 10. I think it's good. All right, so this is my second derivative. So that was part of the problem. Part of the problem is done. The next part of the problem says, describe the region in the xy plane in which, so describe the part of the xy plane in which all solutions are concave down. So what does concave down mean? Concave down means the second derivative is less than 0. So if this is going to be true, then that means that 4/3 x plus 4y minus 10/3 has to be less than 0. I think the normal thing to do here is probably to solve for y. And then, because I'm better at explaining that, like, I don't know, I guess, like I need this relationship to be less than 0. That's like it's not a hard sentence to write. I just don't know like what I'm doing with it. So this would be y is less than, so negative 4/3 x divided by 4 is negative 1/3 x. And then add 10/3, divide by 4 is 10/12, so plus 5/6. Okay, so I think that anytime this relationship is true, so I'm going to say solution curves below the line y equals negative 1/3 x plus 5/6 are concave down. Okay, so where did I get that idea from? So you have this line. Also, I hope that line is right. So you have this line that's like this, right, basically. And since we're talking about y is less than, this is actually like an algebra 1 thing. we're saying like y is less than that. So where is y less than that? It would be over here. So anytime we're below the line, it cuts the plane into two. So you could say the half plane that's below the line, but I'm just going to say solution curves below the line, like whatever. So any solution curves that fall there are going to be concave down. Any that fall above that line are going to be concave up. If you're on the line, you're going to get zero concavity, so you get this linear solution. So the next part of this problem actually says, use your inspire to look at the slope field for the differential equation, plot your solution of part A, and confirm it's correct. So somehow this is going to confirm for us that this is correct. So we're going over to the calculator. Slope fields seem to be one of the things that kind of trigger the calculator to not really be happy. So I don't know. It's really like, of the things that could happen in my life, this is nothing compared to the world right now. But as far as making these videos, like, oh man, not great. Not great that the calculator decided to not play well. So I hate that you can't just use tab when you're in the I don't know, the graph editing thing. Make sure you use y1 and then minus 2. 2/3 x plus 2y minus 2. Okay. I'm gonna press enter. Not a great slope field. So I'm gonna go back. I hit tab again, press enter. You wanna change your resolution here. So it's just bigger. So I usually go with 30. I find 30 is like a nice compromise. Like 60 is not terrible usually. Let me see. It's just you get more lines the higher the resolution. So let's try 60. I mean, it's intense. Okay, so we're supposed to plot what we got for part A. So I'm gonna change back to function. That was menu 3, back to function, -1/3 x plus 5/6. 5/6, that's hard to say. Look at that. So it really does look to me like if we start out below this line, we're gonna get a decreasing concave down solution. If we start out above, it looks like we're gonna get an increasing, not increasing, we're gonna get concave up solutions. They all look like they have a minimum somewhere, which we actually could have worked out. Actually, I can work it out right now. So we would just need dy dx to equal 0. So if dy dx equals 0, you know what, let me just do this. I'm just gonna put in the relation. I need 2/3 x plus 2y minus 2 to equal 0. As long as this is true, if you're along this line, ooh, it's really tight. Everywhere along that line, each particular solution will have a relative minimum. That's a really interesting feature. We're not seeing it very well. I mean, I can try to zoom in. I don't know if this is gonna help. Let's zoom in, zoom in. What might help potentially is if we graphed a bunch of particular solutions. I don't want to do that. I don't want to risk it. I'm going to go back to the notes and see what the next question is, because I think I want to answer that in this video and then break the video in two, because the next part is really interesting and people tend to have a lot of questions about it. So I'm going to break it up so that I can reference specifically that video in the future. So let y equals f of x be a particular solution to the differential equation with the initial condition f of 6 equals -1. Okay. Does f have a relative minimum, relative maximum, or neither at x equals 6? Notice, this problem doesn't say solve the differential equation. It's just saying for this particular thing, are we going to get a relative minimum, relative maximum, or neither at x equals 6? So what I'm going to do is I'm going to take the differential equation, so dy dx, and I'm going to evaluate it at 6 -1, which is going to be equal to, what is dy dx? So it's 2/3 times 6 plus 2 times -1, and then minus 2 is equal to, all right, 6, what do we got going on here? 6 over 3 is 2 times 2. That's 4 minus 4 is 0. Okay, so this is a critical point, right? Because the first derivative is equal to 0. So now what I'm going to do, you never want to do the second derivative, you don't want to do the first derivative test on these, because what does a number line even mean in this context? What we want to do is the second derivative test. So let's do the second derivative evaluated at 6, -1. And this will hopefully tell us, is it positive, is it negative, so are we concave up or down, and then we'll go from there. So let's first evaluate it. So 4/3 of 6 plus 4 times -1, and then minus 10/3. Okay, so we just really care if it's positive or negative. So 8 minus 4 is 4. 4 minus 10/3. So 12/3 minus 4/3 is 2/3. Okay, so I'm going to say since dy dx is 0, and I guess, and the second derivative is greater than 0 at the point 6, -1. Y equals f of x has a relative minimum. So if you think of that slope field conversation where we talked about everywhere along that one particular line, there's a relative minimum, it makes sense that there's a relative minimum. It was either going to be relative minimum or neither. We weren't going to get a relative max because none of the solution types looked like they had that. So a relative minimum at x equals 6. And you could say by the second derivative test, you probably should. I never do. By second derivative test. There you go. All right, so these are all good things to do, right? So it's actually sort of a general principle that this type, so dy dx equals like the standard form of a line, sort of like ax plus by plus c. If dy dx equals ax plus by plus c, there's always going to be a line that cuts that slope field in half. You get like some concave up solution, some concave down. You're either going to get one type with an absolute, well, it is absolute, but one type with relative maximums or one type with relative minimums, but not both. It's a pattern. And the more you do, the more you see. So I'm going to cut this video here, come back in the next video and do this because this next thing is really interesting and it comes up and it confuses people, but it really shouldn't, because once you see how it's done and think it through a little bit, I think you'll be fine with it. So we'll find out, and I will see you in the next video.